Hello, my name is Felicitas Bederna, and I will present our paper Adaptive Compressive Onset Enhancement for Improved Speech Intelligibility in Noise and Reverberation. First, on the background on motivation for our research. In many applications, speech is played back via a loudspeaker in adverse conditions, like in a train station, for example. The speech is degraded by noise and reverberation, resulting in a reduced speech intelligibility. In order to maintain the speech intelligibility, it's possible to pre-process the signal with so-called near-end listening enhancement algorithms. Many of these near-end listening enhancement algorithms process the speech signal for either background noise or reverberation, but as both of these disturbances occur in real applications, we suggest here a combination of two algorithms and examine the improvements through this combination in realistic conditions. We combine the algorithms Adapt-Drc, which was designed for background noise, and onset enhancement, OE, which was designed to process the speech in reverberant conditions. NELE algorithms are usually evaluated using speech intelligibility tests, which require low SNRs to see a difference between the algorithms, because at higher SNRs, 100% intelligibility can easily be achieved. But in realistic conditions, higher SNRs can usually be found. So therefore, we use the criteria of listening effort for the subjective evaluation, as well as for a part of the instrumental evaluations to quantify the benefit of both algorithms alone and their combination. The general NELE task is to modify the speech signal before the modified speech signal is played back via a loudspeaker. In a room, the speech is disturbed by additional noise and reverberation, which can be seen here in this figure. The goal of NELE algorithms is to process the speech in such a way that the disturbed modified speech is audible better than the disturbed unprocessed speech. In practice, we can estimate the background noise and the room impulse response to adjust this processing, but we assume a perfect knowledge in the following. Important to mention in this context is that we apply adaptive processing, so we process the speech signal only when it's really necessary to avoid audible processing artifacts. This is a block diagram of the combined ECHO algorithm, where ECHO is the short form for Adaptive Compressive Onset Enhancement. As it can be seen here, the supposed algorithm consists of the two algorithms Adapt-Drc and OE, which I will describe now in more detail. First to the Adapt-Drc algorithm, which was designed for background noise. It's a two-stage algorithm which combines a frequency shaping stage aiming to enhance high-frequency components and a dynamic range compression to amplify low-level speech components. The algorithm processes speech in small time frames and octave bands. With the speech signal and the noise, a simplified version of the speech intelligibility index is estimated, which controls the amplification stage. A speech intelligibility index of 0, which means that there's no speech intelligibility, results in a uniform distribution of the speech power, so high frequencies are amplified. When the index is 1, no processing is applied. After the amplification stage follows the dynamic range compression, which is adaptive 2. That means for SNRs greater than 15 dB, no compression is applied, while a maximal compression of 8 to 1 is applied when the SNR is smaller than minus 15 dB. After recombination of the subband signals, the RMS power of the output signal is normalized to the broadband input RMS power to obtain the same power of input and output speech signal. The OE algorithm was designed for reverberant conditions, and it reduces the influence of self-masking of speech by its own reflections. It also processes the speech signal in time frames, which are then transformed in the frequency domain. The impulse response is separated in the direct and the reverberant part. The separation time is a constant, and in this case, it's 1.3 milliseconds. The spectrum of the speech signal is then multiplied with the direct and the reverberant part of the signal. The amplification factor is obtained by the calculation of the direct to reverberant ratio of each band, and the band have a bandwidth of equivalent rectangular bandwidth. The direct to reverberant ratio is the division of the direct speech energy by the reverberant speech energy. And the amplification of the speech blocks according to the smooth and limited direct to reverberant ratio increases the consonant to vowel ratio of the speech. A broadband power normalization can be found here too, to maintain the same power of input and output signal. The combination of these two algorithms is the echo algorithm. The main difference between the original algorithms and the two independent parts used in this echo algorithm is the joint third octave filter band to split the speech, the noise, and the room impulse response into third octave bands for the processing. The amplification factors of adapt-GRC and OE are determined separately, and the gain of adapt-GRC is applied first, followed by the amplification of OE. The effect of these three processings can be seen in these spectra of a speech signal. The speech processed by adapt-GRC with the low SNR has much more energy in high frequency regions compared to the unprocessed speech signal. The speech processed by OE looks similar to the unprocessed speech, but the speech pauses are much more pronounced, for example here. Echo is then a mixture between these two processings. It has more energy in high frequency regions, like the adapt-GRC, but the speech pauses are much more pronounced compared to adapt-GRC alone. For the evaluation, we used the following acoustic conditions. We measured the room impulse responses in a room with electronically adjustable reverberation times of 1.08, 2.4, and 4.14 seconds. As a realistic noise type, we used cafeteria noise, which contains both speech and other background noise. For the instrumental measurements, we investigated SNRs between -20 and 20 dB SNR in steps of 5 dB. For the subjective measurements, we selected two realistic SNRs. Firstly, one challenging and noise-dominating condition with a SNR of -5 dB, and secondly, a SNR of 10 dB, where the reverberation is dominant. The speech signals are sentences from the German Oldenburg sentence test. For the instrumental measurements, we used two measures. The first one is the short time objective intelligibility measure, the STOI. The STOI measure is commonly used to evaluate the performance of NELE algorithms because it shows high correlation with intelligibility of noise and time frequency weighted noisy speech. The second measurement is a method to predict the listening effort based on an automatic speech recognition system. The measure corresponds to the uncertainty of the system to determine the phonemes of a speech signal. It shows high correlation for noisy speech, but has not yet been tested in reverberation. We evaluated 10 sentences of the German Oldenburg sentence test that were first processed by the three algorithms and then convolved with the room impulse responses and summed with the noise. The results of the measurements can be seen here in the graph. It shows the predicted listening effort on the left side and the STOI in the right column for all three reverberation times. The expected improvement of the measures with increasing SNR for all three algorithms compared to the unprocessed speech can be seen here. Exceptions are just very high and very low SNRs due to ceiling effects. The improvement was largest for the echo algorithm, but it's very similar to adapt-GRC alone. Remarkable is that the improvements by all algorithms seem not to differ much between the reverberant conditions. For the subjective evaluation, we played back one sentence of the German Oldenburg sentence test in the room with the adjusted room impulse responses and recorded it with the KEMA dummy head. Tests were carried out with 17 normal hearing listeners. And the task was to rate the perceived listening effort on a scale from 1, which corresponds to no listening effort, to 13, which means extreme effort. The method used was modified by the mushroom method. Hence, the listeners could directly compare the processing types in an acoustic condition and rank the perceived listening effort. The results of this evaluation can be seen in the box plots here, where the asterisk indicates statistically significant differences according to Wilcoxon tests. In general, these results are in line with the instrumental results. The perceived listening effort is significantly lower for the by adapt DRC and echo processed speech signals compared to the unprocessed speech. For OE, just a small or no benefit compared to unprocessed speech can be found. And again, the improvements by the algorithms are similar for all reverberant conditions. Now, to discuss these results, it is surprising to see that the adapt DRC algorithm also performs well in reverberant conditions, although it was not designed for that. When comparing the improvement from echo to OE and adapt DRC, it is apparent that echo performs only in some conditions better than adapt DRC. Furthermore, the improvements for echo are similar for all reverberant conditions. This is remarkable because the results of the second hurricane challenge for noise and reverberant conditions showed a better performance for echo in more reverberant rooms, which likely represents the effect of the OE processing and cannot be expected by the adapt DRC algorithm alone. But a comparison between these results and the ones obtained in this paper is difficult because neither adapt DRC nor OE participated in the challenge. But it is clear that further research is necessary to investigate the specific contributions of the adapt DRC and OE part in the processing of echo. In addition to that, the influence of small changes in the room acoustics should be examined. The results also show that the tested instrumental measures can predict all trends observed in the listening tests. Especially the single-ended listening effort measure could yield quantitatively accurate forecasts in noisy and reverberant conditions. This makes it a potentially powerful tool for the comparison of algorithms in realistic conditions and maybe even for online monitoring systems in the future. This was our presentation of our paper. Thank you for your attention and goodbye.